Welcome to Hot Chips 25. Session 4, Interconnects.
Welcome back to the final session of the day. We're going to switch topics away from processors to interconnects. So interconnects really make systems work. We have interconnect topics picked for you that span on-chip NOC technology. We're covering integration of optics into the package. So the marriage of electronics and optics. And we also talk about switching technology in a data center. And we're looking at rack level, backplane, interconnect technologies as well. Our first talk of this session is by Luxtera. The first speaker, Peter de Dobbelaere, received his PhD from University of Ghent in 1995. Then he started working for a company called AkzoNobel, where he was working on waveguides. Then he switched to working in the US, a company called OMM in San Diego, where he worked on MEMS-based optics. And then he finally switched over to silicon photonics at the company he's at right now, Luxtera. And he has a quite exciting talk today. He's going to cover basically how the silicon photonics space is evolving, covering the trade-offs, where is the electrical domain, where is the optical domain, and how these domains will come together. And finally, will give us a look at upcoming interposer technology that allows us to marry really electronics and optics using silicon photonics-based interposers. So Peter?
Thank you, Ralph, and thank you for inviting me over to give this talk on our work at Luxtera. Here's a short overview of what I'm going to talk about. First, I start with an introduction on silicon photonics, because it's probably here for the public a new topic. We'll explain a bit what the technology is and what it can do. And then the second part of my talk will be about the application of silicon photonics for optical interconnect, and specifically for integration with ASICs. So this is a kind of a busy slide. It talks about silicon photonics technology itself. So basically, silicon photonics is a technology that makes use of the silicon material system, silicon CMOS processing technology to build optical and photonic devices. Development in earnest started on this technology in the early 2000s. Intel and IBM were two companies which started this development. But also Luxtera at that time was founded, and we started to work on that as well. And many other companies have followed after that. So what is the goal of silicon photonics? Is basically leveraging as much as possible all the investments that have been done in the CMOS industry to manufacture photonic devices. And leveraging that goes from the processing technology, goes from the design environment, goes to the test infrastructure, packaging methodologies, and so on. Also, what silicon photonics is kind of promising is that you can, and similarly to the electronic CMOS industry, is try to integrate a lot of functionalities in a single chip. So a very high level of integration, which should also result in a cost reduction and an increased performance and functionality capability. Applications, I mean, there are many applications of silicon photonics. Here I will only address the high-speed interconnect aspect of them, but there are many other ones in medical sensors, in motion sensors, in analog computing, and so on. I won't address that. And then a little word about Luxtera. So we have been producing silicon photonics devices already since 2009, and we have been shipping them in real applications, mostly in InfiniBand high-performance computing systems, but nowadays also in Web 2.0 data centers for longer reach applications. And currently we are developing IP chipsets and transceivers for high-speed interconnect, and we are working with partners on integration of silicon photonics with ASICs. A little bit about silicon photonics technology itself. So we have something about wafer manufacturing. Processing is done on SOI wafers. We have 2 foundries we are working with. We started with Freescale, a very good partner, and recently we also started to work with ST Microelectronics in Crolles in France, where we are bringing up a process. We have, within the process that we have there, we have the definition of waveguides by lithography and etching. We have selective epitaxy to make monolithic photodetectors, and we have also active devices by using implants. Using that technology, we have a device library, just like you have in the electronics world. We have photonic devices, waveguides, splitters, couplers for light in and out of the chip, phase modulators to modulate the light, and waveguide photodetectors. All of that, the library and the wafer manufacturing is then going into a design kit, which is cadence-based. We have a complete flow that enables us to design full chips within that cadence flow. We have behavioral models of the devices, so with the process corners, so that we can really design a chip just like an electronic IC designer would do. We have LVS decks, we have DRC decks that can check for the manufacturability and the proper design of the circuits. And our chips, our product chips, are all designed, I must say, by electronic engineers. There are no photonic designers around there. The photonic designers work on the device library. The electronic designers are working on the real circuit chips. Very short, I go very quick over this. A word about how we modulate light, because that's an essential part of making an optical transceiver. The key device that we use for that is an MZI modulator, Machtzehner. So basically you have one input, you split the light in 2 arms, then you combine them again, and then you do something with the phase difference between the 2 arms. Is it in phase, you have light coming out this arm, is it out of phase, comes out of the other arm. If you take only this output, you can switch the light on and off. That's basically how we modulate the light. Here, for instance, you see a circuit where you have here the electrical inputs, electrical receiver, a driver, and then here a 28 gigabit per second MZI modulator. Same thing at the receiver side. We have, in our process, we have germanium photodetectors, which are made by epitaxy of germanium on a silicon waveguide. We have contacts on that, and we can make, hence, a photodetector. With a very good performance there, we've shown more than 50 gigahertz bandwidth, which is more than you need for a 50 gigabit per second transmission. And again, you see here the circuit. Here is the germanium photodetector, very small. You can't see it here on the picture. It's only 2 by 10 micron in size. Then you have here the electrical amplification stages, and then the electrical driver of the wire bond pads of the chip. So these are then coming together in a transceiver chip. This is our 4 by 28 gigabit per second transceiver, so more than 100 gigabit per second transceiver in a single chip. Here you can recognize the 4 transmitters, and here the 4 receivers. Here is a digital block that takes care of the control system and the communication, because there are many monitoring points in here, and through the I2C interface we can send out the monitoring signals to whatever is needed on the outside for the diagnostics. Something that I didn't talk about is the light source. So you know that for silicon photonics, I talked about a modulator, a photodetector, and waveguides. But where's the light coming from? Well, the light is coming from something like this. We call that lamp. It's a laser micro package. Basically, it uses an off-the-shelf laser diode chip packaged in a silicon housing, and that is placed on top of the silicon photonics die and is beaming light into the chip. That is our light source that we have, and we built transceivers with this, and we had error-free performance and demonstrated interoperability with many other people's high-speed I/Os. What I showed you before, that was a chip where the photonics and the electronics were all integrated in the same substrate. So we had transistors sitting next to optical modulators, waveguides, and photodetectors. And we call that the monolithic integration. It's a single chip solution, obviously. It can have the shortest interconnects between the photonics and the electronics, so that can be advantages. For instance, if you have a low capacitance between a photodetector and a receiver circuitry, you can have a higher receiver sensitivity. That can be advantages. The process is more complex, of course. Sometimes it's not area efficient. If you put photonics on electronics, you can imagine if you are in a 22 nanometer process and you put in there large photonic devices, that the real estate is very expensive there, so that's something you have to consider if you want to integrate monolithically. And the one that was driving us the strongest was that if you want to go to a more advanced CMOS node, and the case that we had here, for this chip, it was a 130 nanometer node, and running that at 28 gigabit per second, that's really pushing it. If you really want to go to a more advanced node, like the 28 nanometer node, doing that monolithic, developing that monolithic process is very expensive, very expensive. Therefore, we look to another approach where we break the system up in two pieces. We have a photonic die and we have an electronic die. The photonic die is optimized only for photonics, and the electronic die can be from any node. So, for instance, can come from a 28 nanometer node, come from a 22 nanometer node, or even by CMOS. You have a decoupling of the two technologies. You have a very efficient use of the area, of the expensive area in the advanced electronic node. And it becomes more straightforward to integrate third-party IP. But for instance, we are currently developing a product where this electronic IC is designed in TSMC 228 HPM. There are many other companies developing IP in that node, so it becomes more straightforward to integrate it with our silicon photonics. Something about scalability of silicon photonics. For instance, currently you are working on 28 gigabit per second, but what comes beyond that? There's, of course, the data rate. Can we go to 50 gigabit per second? And from what we see from the modulators, from the photodetectors, there is no issue there. I mean, we have the modulation is determined by the RC time constant of the device itself and has like 45 gigahertz electrical bandwidth. The photodetectors are sitting at more than 50 gigahertz bandwidth, so that is also no problem. And for the electronic circuits, of course, we will have to use a node that has a high enough FTs for the transistors to make those work at 50 gigabit per second. Another area of scaling for optical transceiver technology is the density. That means how much transceivers can you put per unit area. Actually, we saw that most of that area is determined by the optical I/O, how you get light in and out of that chip. A very standard distance between fibers, for instance, is 250 micron. That is, of course, huge. And that is why we have been looking, and also others have been looking at, how can we cram more data in a single fiber core. And one of the most famous ways to do that is using wavelength multiplexing. You have different wavelengths, you modulate them individually, then you mux them together and send them through a single fiber. That works. I mean, we demonstrated that already in 2007. Other companies have followed us as well. But it is more expensive since you need 4 lasers. And lasers are kind of more expensive than, indium phosphide is more expensive than silicon. So some people, and also we came up with the idea, we can actually use a single laser and use pulse amplitude modulation, or use any other modulation format. And actually, the discussions went pretty well forward there in the IEEE standards for the 100 gigabit Ethernet and 400 gigabit Ethernet to look at pulse amplitude modulation. Comes out that silicon photonics and the way we implemented it lends itself very well to pulse amplitude modulation. You can build out of that MZI very, very easily, a PAM encoder, for instance. Another technology that we have been looking into with some partners from the fiber industry is multi-core fiber. So that is a fiber which has multiple cores in it. So that also allows you to have in one fiber multiple signals. And using our specific technology that we have developed to couple light in and out, we can actually couple very efficiently light in such multi-core fibers. So that is also a route for us to go to higher density. And now I come to the second part of my presentation. That is what we see in the high-speed interconnect world. We see obviously the need for higher data flux, and that is currently limited basically by how many bumps you can put on a package. For instance, for some switch devices, like the number of bumps is limited to about 2,500. And the only way to get more data in and out of that switch chip is by increasing the data rate. That's why you saw the evolution from 10 gigabit per second to 25, and then you hear people say, well, we have to go to 50 or 56 gigabit per second I/O just to get more data in and out of those switch chips. Another limitation comes actually from the faceplate density. So basically, those guys go in a shelf like this, and then the optical I/Os are sitting normally in the front. So you need a routing of electrical signals from that switch chip that is inside here to the transceivers which sit in the front. That faceplate density is also a limiter for the density of how much signal you can get in and out of such a switch shelf. So increasing that density is an important factor. Solutions, I already mentioned that, is going to just to higher data rate. And another one is to integrate optical I/Os closer with the ASICs. And I will talk later about that, why that is an opportunity. Another one that goes together with the density here is that the power dissipation needs to come down. For instance, the size of an optical transceiver is to a large amount determined by how much power it dissipates. So for instance, for a QSFP optical module, going above 2.5 watts per module is too high. If you want to have higher power dissipation, you have to go to a larger module on which you can put a larger heat sink, but hence your density is decreasing. So that is kind of an important thing you have to look at. Power and density, in a way, go together. So how can you reduce the power dissipation? A big driver, as we see in the transceivers, is the signal integrity and the electrical I/Os that you need to overcome them. For instance, you need repeaters or CDRs or whatever, and those are all dissipating power, in many cases much more power than the optical transceiver itself. So if you can reduce the requirements for those repeaters or retimers, you can reduce the power dissipation. And ultimately, if you could integrate photonics with electronics without any trace in between them, so there is no signal integrity issue, you can take all these electrical I/Os out, and you can even much lower power dissipation. That will be one of the things that I will address later on. Another trend that we see is that interconnect lengths are getting longer. And that's specifically for these large data centers where there is a significant market for optical transceivers. Those data centers are getting very big. You see here kind of a picture of a data center made by QTS. And interconnect lengths can go up to kilometers even. And silicon photonics by itself lends itself very well for error-free, high-speed communications in such data centers. Now, if we look back to what I just mentioned, currently we have these optical transceiver modules in the front of a shelf. And hence, I already mentioned if you have a switch there, you have to route all those high-speed signals to the front. The advantage of that technology that we're using today is that you can use MSA-compliant modules so that you can have many suppliers. But you have the signal integrity issues. You have the need for SerDes in the ASIC, a retimer on the PCBA, or a retimer in the module. And hence, you burn a lot of power. And you see here, we estimate at about 1.75 watts at each end of the electrical link, and the optical module at 0.9 watts. That's all for 100 gigabit per second. So the total is like 4.4 watts for a 100 gigabit link. What we now see that many people are coming to us asking not, we don't want to have this, we want to actually make that trace on the PCB shorter, and they want to put optical transceivers around the switch so that these traces are shorter, so they can maybe take some of the retimers out and bring the high-speed signal optically through fiber to the faceplate. That is definitely an advantage for reducing the power dissipation. As you can see, we get here a little bit more than a watt lower in power dissipation, but it makes the user friendliness a little bit less, since you cannot easily replace those devices. You have to open the shelf, and if one of them fails, you have to take it out and replace it. Hence, there is a very high reliability requirement for those. And that is also an important aspect there, that once you put the transceivers inside the box, the reliability requirements becomes very strong. The next step, and it is for beyond 2015, is where actually we integrate the transceivers that are sitting here around the switch chip actually in the switch. So we co-package the optical transceivers with the switch chip, for instance, or the ASIC. Pretty much the same holds here as what we had here, but the reduction in power is very large. I mean, you go here to 1.7 watt, even if you include a 0.7 watt for a SerDes in the switch chip. So that means that the biggest bang for the buck, you can have the largest power reduction if you go this path. And silicon photonics allows you actually to do that very efficiently. So here is a first way you could do that. This is a walk before you run. It's actually depicting what we are currently developing as a transceiver product. So basically, we have a silicon photonics die, photonics only, and then there is an electronic die mounted on top of it. Interconnect is with the copper pillar technology to interconnect the electronic circuits with the photonic circuits. The light source is also put on top of this, the photonic IC. And if you look at that electronic die, it has actually two pieces. One of it is specific IP for driving the photonics. The other one, the green one, is just the electrical I/O with CTLEs, CDRs, and all of that. It's very standard here. So you can imagine if if a customer comes and say, hey, I have a very interesting IP, I have a special I/O, I have a gearbox, or I have a special SerDes, and I have developed that in the same node as we developed this chip in, that actually new IP can be added instead of the IP that we originally had in our transceiver. And hence we can make kind of a customized optical transceiver. So this is a first example. And of course, if you would integrate that in the old way with two different packages, you would dissipate a lot of more power. And here you see, this is here just an example of the IP blocks for a transmitter. So here's, for instance, our block that we usually have as a transceiver. This is the electrical I/O. The blue devices are the silicon photonics specific electronic circuits, and here the pink color is just the photonic devices. Here in this case, these are the phase modulators. At the receiver, it's very similar. They have a photodetector and receiver circuitry, and then electrical IOs as well. The last part of my talk here is about ASIC integration by means of a silicon photonic interposer. And what it actually is the combination of the technology of the electrical interposer that has been presented, for instance, by Xilinx, TSMC, and Amkor, and combining that with silicon photonics. And what you see here is kind of the interposer that I took from a picture from that team here. And here the yellow line is the layer with photonics. It has the waveguides for the routing. It has the modulators. It has the photodetectors. And they are driven, just like I mentioned before, by an electronic chip, an ASIC, of which certain circuits are replaced and are driving the photonic devices. Doing that, obviously, you can get, as I mentioned before, a significant reduction in power, a significant reduction in size, because you see you have that switch chip with before all those transceivers sitting around it, all these collapse into a single package. We can integrate different technologies, obviously. It can be, as I mentioned before, because it's with that hybrid integration, you can go to any node. We can also use external light sources. You don't necessarily have to put light sources on that interposer. You can actually bring the light in from a remote light source with a fiber. And as I already mentioned, silicon photonics technology itself can go 50 gigabit per second and beyond. Here you see kind of how that could look like. So here, this green here, this green board is the host PCBA, is the big PCBA. Then the other lighter green is the package substrate of the silicon photonics interposer. The silicon photonics interposer is here, this gray rectangle. You can see it here as the blue. The ASIC itself, for instance, the switch chip, is sitting right here. This is the green chip. And these special elements here are the optical interfaces. They allow the high density interface of light from fibers towards the silicon photonics interposer. Interconnect between the interposer and the ASIC is by means of those copper pillars. And as you see on the ASIC, what has happened there is that we have replaced the IOs that are driving the bumps and driving then the transmission lines on the PCB. We replaced them by circuits that we have designed that drive actually the silicon photonics modulators and receive the light from the photodetectors and amplify. And this is a kind of our vision for the ultimate optical interconnect. So coming to the summary, I highlighted our technology, a short introduction of what we can do, and that we can reach very high interconnect densities at low power dissipation. We have been shipping silicon photonics already since 2009 in volume, and they are currently used in high-performance data centers and high-performance computing applications. I discussed a little bit about the hybrid integration, why we went from the monolithic integration to hybrid integration, actually to allow us to be more compatible with where other third parties are developing their IP, and also to reduce the development costs. We showed that we are already talking with partners on integrating their IP with our optical transceivers, and also I showed that in the next level we see for ASIC integration a silicon photonics interposer as the ultimate for integration of photonics with ASICs. And that concludes my talk. Thank you very much.
Thank you, Peter. Really enjoyed the talk. We have time for a few questions.
Hi, Peter. Gary Fleeman with Advantest. Any comment you might make about alignment for lenses or something when it comes to packaging on the substrate or on the multi-chip module? Something to say about that?
Yeah, actually, I didn't talk much about that, but we have a lot of technology development in that area. The alignment is a single mode alignment, and also there, for assembly, we are using tools from the semiconductor industry. So that is one of the other elements that I mentioned, both for test and for optical assembly. We want to leverage what is available in the industry.
Thank you, sir.
Hey, Zhen Li from Samsung. So I have a question about thermal stability. So let's say if the ASIC chip is dissipating lots of power and like fluctuate the temperature a lot, would that affect the stability of the external like indium phosphide light source? Or how would that affect the transceivers and detectors?
Correct. First, about the light source. Indeed, indium phosphide laser diodes are more sensitive for temperature variation. That is why in this application, where things can get really hot, we can put the light source remote in a place where it's nice and cool and bring the light in with a fiber. But also in the case where the laser is closely integrated with the silicon photonics, we have, and in the transceivers that we are currently shipping, that is the case, we have control systems in place that keep the output power constant, that keep everything running as the standards require. So there's also an aspect that I didn't address here. There's a lot of control system work also in the design of our chips. When you look at the silicon photonics themselves, I mean, I'm talking about the modulators and the photodetectors and the waveguides. Those are actually very insensitive for the temperature. There is some variation possible, but yeah, we learned to cope with that. I mean, up to 100 degrees C is not a problem for us.
Thank you.
Welcome.
Bob Masley, Oracle. Peter, what is the latency that you're seeing from electrical, optical back to electrical, the total latency?
Ooh, I think it's mostly the speed of the light. If you go through the fiber, it's I think 5 nanoseconds per meter. Within the silicon photonics itself, it's in the order of picoseconds, I believe. I should check, but of course, if you put CDRs in, you get some UI for that as a penalty, but it's definitely not something that is very high.
Thank you, Peter.
You're welcome.
Hi, Mark Grossman, Microsoft. Just afraid to ask, but cost, say per gigabit or per, gigabit per second for, say, at the boundary of a chip, compared with conventional, all electrical.
Yeah. We want definitely to be competitive with the other technologies, and we are. For instance, with the AOC business, we were definitely with silicon photonics competitive with other technologies. And we hear a lot from our customers that they want to be below $1 a gigabit, and we think we can definitely get there.
Thank you again, Peter. That was a great talk. Thank you. Now we switch from package level interfacing of interconnects to silicon to on-chip interconnects, and we have the opportunity to hear from Sailesh Kumar. So Sailesh is with a new NoC company. Some of you may remember Sailesh from 3 years ago when he was actually working at Huawei. He was actually working on the 100 gigabit network processor with advanced integrated memories. From that job, he's actually learned quite a bit about interconnects and requirements, and he's actually jumped into helping start a company focusing on improving NoC technology. And he's here to talk about his new role at NetSpeed Systems today.
Thanks a lot, Ralph. I'm Sailesh Kumar, and I'm from NetSpeed. NetSpeed, we started this company in 2011, and all we do is NoCs, on-chip interconnects. And today we are going to talk about NetSpeed Orion, which is our first interconnect IP solution, and we are going to give you more details about this today. So So on-chip interconnect is becoming more and more important with time in SoC space because of three main reasons. The first reason is number of components on silicon is growing rapidly. Over the last few years, it has grown from a few tens to a couple of hundreds. And this number we got from a typical SoC used in tablet processors. Second trend is that as SoCs are becoming more and more complex, and as we have more and more components, on-chip communication is becoming more and more complex. There are more complex quality of service requirements, there are more complex deadlock scenarios, and there are many more protocols running on the same SoC. And therefore, the on-chip interconnect design is becoming much more complex. Third trend is people are using more and more off-the-shelf IP components. So building an SoC to a large extent is using off-the-shelf IPs and building the interconnect that will satisfy all the requirements of SoC. So because of these three trends, on-chip interconnect is becoming more and more challenging and more and more important. So if you look at interconnect design, network on-chip is a popular, or I will say a more systematic approach to do on-chip interconnect because network on-chip approach scales very well, and also it can maintain very high performance. Now, if you look at network on-chip design, it contains three major elements. The first is architecture, which includes aspects such as how to decide the most optimal topology, how to map your traffic to various NoC elements, what is the right route that I have to pick to get an optimal architecture. So these are the architectural aspects. Then you have to use some innovative algorithms to make sure that your network is correct by construction. You have to make sure that your network maintains end-to-end quality of service properties because quality of service is becoming more and more important in modern SoCs. Moreover, you have to use algorithms to make sure that the interconnect is deadlock-free and correct by construction. So these are the algorithmic aspects. And finally, you have to use the hardware elements to build the interconnect. Hardware elements include routers, switches, channels, protocol bridges, and so on and so forth. Now, if you look at today's commercially available NoC solutions out there, they focus on hardware. They don't really provide the end-to-end solution. So if you look at these solutions, they provide a Visio-like platform and all the hardware building blocks, and they expect user to manually build the interconnect. They expect user to solve the architecture problems. They expect user to make sure that the interconnect is correct by construction, which is very challenging, actually. So I'll give you a simple, I used to work at Huawei earlier, and at Huawei, we did a very high-performance network processor where there were like 200 cores on a single chip. We spent a lot of time. We designed all the elements, processors, accelerators. But when it came to connecting all these components together, we spent, I will say, more than 20 man-years in building the interconnect, and still we were not satisfied with the on-chip interconnect architecture. And at that time, basically, I had this idea that why don't we automate the whole thing? Why don't we have a solution where we can build an interconnect that is correct by construction and that can scale seamlessly? And that's how NetSpeed started. So at NetSpeed, we are trying to address all the three key challenges of interconnect design: architecture, algorithms, and hardware. So our solution can address the concerns such as what is the right topology, how to map traffic to the topology, how to make sure that the interconnect is correct by construction, and how to make sure that the interconnect design is efficient. So we'll talk about NetSpeed Orion, which addresses all these three concerns. So as I said, at NetSpeed, we have come up with a very systematic, fully automated architecture that can automatically decide the right topology based on high-level SoC requirements. So user can specify the high-level interconnect requirements, such as bandwidth, number of components. Based on this, we can automatically decide the right NoC architecture for a given SoC. Our architecture is physically aware, so we take floor plan information and we generate an interconnect that is physically aware and correct by construction. We also map the SoC traffic to the interconnect elements and make sure that latency, power, area, everything is optimized. So the whole architecture is fully automated. We also leverage state-of-the-art algorithms to make sure that the network is correct by construction again. And we have integrated quality of service properties and deadlock avoidance to make sure that network is deadlock-free at both network level as well as a protocol level. And we also maintain end-to-end quality of service. Now, as a result of these state-of-the-art algorithms and efficient architecture automation, we believe that our solution will give you the most optimal design. It will be highly efficient, and because it is physically aware, it will also give you optimal latency and optimal bandwidth. And as a result of all these advantages, you can get massive time-to-market advantage by using our solution. So this slide kind of gives high-level overview of the design flow of our solution. The design platform that we have is called NoC Studio. And these are the 3 high-level steps that user uses to use NoC Studio. The first step is specification of the requirements. So here, user specifies the floor plan. They specify a number of IP components that they want to integrate, bandwidth requirements, latency requirements, quality of service policies, and some protocol information so that we make sure that interconnect is deadlock-free. Once the specification is provided, using NoC Studio as an interconnect architecture exploration platform, user can build various types of interconnect architectures automatically, benchmark the performance, look at the cost, look at the performance. NoC Studio has a cycle-accurate performance simulator built into it, using which any interconnect design that is either automatically generated or customized by the user, you can benchmark the performance, you can look at the cost, you can look at the power consumption upfront. And once you have the final interconnect architecture in NoC Studio can generate the IP in terms of RTL files, in terms of test benches, in terms of performance statistics, in terms of documents, and in terms of test benches. So it's a very high-level flow. In addition to all the automations, we have provided hooks to users so that users can control the architecture. They can customize the resulting NoC. So I will say it's fully automated, as well as we provide user sufficient control for the user to control the architecture. So this slide kind of gives the high level again picture of the design flow, and we are going to talk about the specification phase. So our interconnect architecture is physically aware because you have to make to make an optimal interconnect. You have to be aware of the floor plan of the SoC. So during a specification, we expect user to specify the floor plan of the SoC using a 2D reference grid. So user adds all the components in a 2D grid. And then user specifies the traffic requirement, bandwidth requirement, and based on these specifications, based on the floor plan, NoC Studio automatically generates a baseline interconnect. So our baseline interconnect is correct by construction. So here is a video shot taken from NoC Studio, where user specifies the requirement, specifies the floor plan, and based on the initial specification, NoC Studio generates a correct by construction NoC that meets all the requirements. So this is a baseline NoC. This NoC is not yet optimized. So second step is optimization of the NoC. So now we are going to go to second step. So during this step, user basically provides their optimization goals. User can optimize the NoC for performance. They can optimize NoC for latency. They can optimize for low power, or they can optimize for the cost in terms of wire cost and buffer cost. So during this step, user interacts with NoC Studio, provides various optimization goals, and NoC Studio will automatically optimize the NoC topology, optimize the NoC architecture, optimize the routing algorithms that are used, and it will generate various types of interconnects that are all correct by construction and that have different characteristics. Using cycle-accurate performance simulator, users can benchmark any NoC architecture. They can look at the performance, they can look at the cost, and they can decide the right architecture for themselves. So it's a fully automated flow. At the same time, as I said, users can customize any given architecture. So any architecture that NoC Studio produces can be customized by the user. User can also provide a bunch of constraints to make sure that NoC meets the constraints that user has provided. Finally, once the NoC is designed and optimized, NoC Studio can go ahead and generate all the IP files, which includes RTL, includes C++ models, cycle-accurate models, test benches, and a bunch of documents and performance statistics. Right? So this is high-level design flow of NoC Studio. Now I'm going to go to the second part of the talk, where I will talk about some of the key challenges that we faced during design of our NoC solution, and what kind of innovations we have done to solve these problems. So the first challenge is automation of the architecture, automation of the NoC topology. Now, this is a very challenging problem. NoC topologies have been studied a lot in the past. A large number of architectures have been proposed: mesh, tree, bus, multi-stage class networks. So all of them are very well-studied topics. However, if you look at one common thread across all these topologies, they are very symmetric. They are very homogeneous architectures. However, a typical SoC is not symmetric, so it becomes challenging to use a textbook NoC architecture and map it to a given SoC. Even if you find a way to map a standard topology to a given SoC, you still have questions such as is this NoC correct by construction? Is this NoC going to meet my quality of service requirement? Is it efficient design or not? So this is a fundamentally difficult problem to solve. And we have innovated a lot here, and we have come up with machine learning algorithms, unsupervised learning algorithms, to automatically determine the most optimal topology for any given SoC requirements. So user provides the specification, we automatically decide what is the most optimal topology based on the specification. And our topology is completely adaptive. We can become a mesh. We can become a ring. Based on the specification, we will automatically generate the most optimal topology. Not only that, shape and size of our topology is adaptive. Every element of the NoC topology is adaptive. We optimize every buffer. We optimize every channel, every wire of the interconnect. So if your bandwidth requirement is highly heterogeneous, not only that our topology will be heterogeneous, every element will also be heterogeneous. So everything gets optimized. As we generate these interconnect architectures, we make sure that the interconnect is physically aware. So we take floor plan information upfront, and based on the floor plan information, we generate an interconnect that will naturally map to your floor plan. So this will give you the most optimal performance, most optimal efficiency, and I will say most optimal latency as well, right? So based on any given floor plan, we will generate a physically aware, highly optimized topology automatically, and topology gets completely optimized. Every buffer, every channel is optimized. Now, in addition to building physically aware NoCs, we have also added tools to NoC Studio to give feedback to user to improve their floor plan. Because NoC architecture is so much tied to the floor plan, if you have a wrong floor plan, you will not have an optimal NoC. For example, if two agents are talking to each other a lot, and if they're far away in the floor plan, you will not get a very efficient NoC. So building the right floor plan to optimize the interconnect is actually a known NP-hard problem. This problem has been well studied in the past. So here again, we use heuristic algorithms to give feedback to user about how to optimize the floor plan. So using NoC Studio, users can actually improve their floor plan and then generate physically aware interconnect. So they will get even more benefit, and they will be able to generate more optimized interconnect. As I said, this is a known NP-hard problem. And again, we have done a lot of innovation on the algorithm side to make sure that our solution gives you most optimal results, as well as it is correct by construction. Now, in addition to these optimizations, the way we have defined our architecture is our architecture scales naturally. And we have different degrees of scaling, and NoC Studio will automatically leverage the right scaling to build an efficient interconnect. So we can scale in terms of number of nodes in a single NoC layer. So if your SoC is scaling or if your bandwidth requirement is scaling, we will automatically increase the size of network. So that's one type of scaling that we can do. Second type of scaling is vertical scaling, where we can automatically increase the number of layers. We can allocate multiple parallel networks, and therefore we can add more connectivity or more bandwidth. So NoC Studio can automatically decide what is the right scaling required for a given SoC and for a given floor plan and for a given requirement. So therefore, we will automatically allocate the right number of layers. Every layer will get optimized, and as a result, you will get a highly optimized interconnect architecture. So we also leverage these two types of scaling, and we automatically decide what is the right scaling for a given requirement. Now, here are some results of NoC Studio generated NoCs. So when we compare our baseline NoC to a standard, for example, AXI interconnect, our baseline NoC itself is much more efficient. It has less wires compared to a standard AXI crossbar-based interconnect. Once you do all the optimization algorithms, once you optimize the channels, once you optimize the topology, you will get further reduction in the cost and further improvement in the efficiency. So what we have seen in like typical use case is we are 50% better. Our baseline interconnect is 50% better than AXI interconnect, and you can get up to 60% improvement using the optimization algorithms. Our hardware library also scales in terms of clock frequency. The way we have designed our hardware elements is our NoC can scale to up to 2 gigahertz in clock frequency in 40 nanometer. So now we'll talk a little bit about the algorithms that we have innovated in designing this NoC. So as I said, our NoC takes high-level specification and makes sure that the auto-generated NoC is correct by construction. So there are two key challenges that we faced. How to make sure that NoC is deadlock-free, because more protocols are becoming more and more complex in the SoCs, plus the size of network is growing, which makes deadlock more challenging. So there are two types of deadlock. There's network-level deadlock, and there's protocol-level deadlock. Now, in NoC Studio, if you provide all the protocol information, we guarantee that by construction, our NoC will always be deadlock-free, both at network and protocol level. Now, avoiding deadlock is very challenging in an environment where the topology is highly heterogeneous, the floor plan is highly heterogeneous, and you have a lot of different types of protocols running in the same system. So far, in all the existing commercial NoC solutions, users have to manually make sure that the interconnect that they generate is deadlock-free. We have fully automated this process, and our NoCs are always deadlock-free by construction. Second key challenge in NoC design is to make sure that end-to-end quality of service goals are met. So quality of service is becoming more and more important today. And quality of service is about providing fair allocation to all the resources on the SoC. It's also one important goal of quality of service is to make sure that your solution is low cost. And it doesn't really increase the latency of the interconnect. There are a bunch of well-known quality of service techniques that have been studied, used in the past. Most of these techniques have certain disadvantages. Either they're not fair, or if they're fair, the cost can be very high, or maybe they're not very fast to react to changing traffic profile. So again, we have done a lot of innovation on this side. We have come up with low-cost, highly efficient algorithms that can provide sophisticated quality of service properties to interconnect and still make sure that the interconnect is deadlock-free, is correct by construction, and it can react to changing traffic profiles very quickly. Not only that, our quality of service algorithms are efficient and sophisticated, they're also fully automated. So in a typical design flow, users have to design the interconnect, maybe put quality of service hardware elements, and then go and back and forth tune the hardware elements to make sure that the quality of service requirements are met. So at NetSpeed, we have fully automated this process as well, where users can specify the quality of service requirements, end-to-end quality of service requirements at higher level, and we generate an interconnect that automatically enforces end-to-end quality of service properties. Here are some simple results. Again, we have more comprehensive results as well, but here I'll just show some simple results. So here I have got a single memory. I have got a highly irregular NoC topology. I have got 8 CPUs talking to that memory. And we want to divide the memory bandwidth in certain ratios among these agents. So we generated NoC. We specified the quality of service requirement. We generated RTL, did RTL simulation, and we found that our NoC is indeed able to maintain end-to-end quality of service properties. In the second simulation, what we did is we changed the activity of these agents. Some agents were active at some points, some agents were not active at some other points. So even in spite of very quick active and inactive state changing, what we found is our interconnect is actually able to maintain full fairness as well as it is work conserving, in the sense that no matter what in what order agents are becoming active and inactive, we are able to keep the memory busy as long as we have sufficient number of transactions initiated for the memory. So we are both work conserving, quick to react, as well as we are fair. As I said, we have more comprehensive results as well, and to our customers we also show more comprehensive results of quality of service. Now, the last challenge of building an interconnect solutions like us is verification. Our architecture is, we have invented a lot of algorithms, we have a lot of automation, and our architecture is fully adaptive. So how to make sure that even if our algorithms are correct, how to make sure that the implementation is correct, how to make sure that the NoC that we generate is correct by construction. So to address this, we have very comprehensive verification strategy. So we have a 3-tier approach. Every NoC element, every hardware element that we use in building the NoC is verified at module level, and we have very good coverage here. We have actually 100% coverage. Every hardware element is verified at module level. And then we have NoC level functional verification environment, where every day we generate, I will say, thousands of random NoC configurations, and we functionally verify the generated NoC. We augment this verification with emulation. We use Cadence Palladium boxes to do emulation, and every night we run hundreds of millions of packets through our NoC. So we have fairly comprehensive verification strategy to make sure that our NoC is functionally correct. Now, how do we stack against the competition? So here, I have listed a bunch of NoC design elements, such as topology, quality of service, and those blue dots over there are different design points that someone might use. So based on our knowledge, what we have seen is most of the commercially available designs, they are generally on the left-hand side. So here, a design point on the left-hand side is generally less scalable and less efficient, and a design point on the right-hand side is more scalable, more efficient. So what we have seen is, in every aspect, our design is much more efficient, is much more scalable compared to every commercially available solution today. So this is the last slide that I have. So to conclude, we truly believe that our solution represents a quantum leap in NoC design, in automated NoC design. Our solution is fully automated, highly algorithmic, efficient, and correct by construction. Going forward, we are adding cache coherency feature to our NoC so that users can generate fully cache coherent NoCs. As a result of these innovations, we believe that users can get highly optimized design using our flow. They can get substantial time to market advantages. They will be able to generate high performance scalable interconnects at lower power. And not only that, we believe that our solution can be a platform for architecture exploration, which will create new possibilities for the customers where they can come up with new SoC architectures and new interconnect architectures. So with that, I would like to conclude my talk, and I can take some questions now.
Thank you, Sailesh.
Yes, Satoshi Matsushita, NEC. I have a couple of questions. Do you support a multi-path network with which cause out-of-order packet arrival?
No, so we don't do dynamic routing. You're talking about dynamic routing, I think. So we don't do dynamic routing. Routes are static. But to select these routes, we use algorithms to make sure that the statically chosen routes that we have are load balanced, are efficient. Because dynamic routing has a bunch of challenges. I mean, dynamic routing has been studied a lot in academic world. But to my knowledge, I mean, I don't know of anyone who actually is using dynamic routing in a real world system.
Okay, and the second one is what is the API, the interface is seen from the each IPs, like
yes.
handshaking or something?
Yeah, sure. So today we support AMBA4 and AMBA5 protocols completely. So all the AXI interfaces we support, ACE interfaces we support. And we also have defined our own streaming protocol, which is a very efficient packetized protocol, very similar to AXI streaming protocol. And a lot of our customers are actually using that protocol because that protocol has been designed for very high efficiency. So it's a very simple protocol where you stream data into NoC, and you also get a streaming data out of the NoC. So we support these two protocols today.
And even the protocol is different from one IP from the other one, each one can communicate.
Exactly. We support multiple protocols simultaneously as long as the agents who are talking to each other have the same protocol.
Okay.
Yeah.
Thank you.
Hey, Jenny from Samsung. I have a question about the coherent thing you mentioned in the last slide. So let's say, like if you use the XI bus, like the processor can address like all its peripherals in the same physical address. But if you're using like this kind of eNoC, how do you handle the overhead of doing such kind of convenient like programming model?
Yeah, so for coherency, today we support AMBA protocols, ACE and AMBA5 protocols. So ACE coherency is weakly consistent. So basically, the way we have designed our architecture is, as long as you have ACE agents and as long as you have AMBA5 agents, our interconnect will satisfy all the ordering requirements of an ACE agent. We don't have a strongly ordered model today because our architecture is completely based on ARM protocols.
Okay. Do you have any performance numbers like about those things?
On the coherency side? So as I said, our coherent NoC will be released by end of this quarter, so probably in September, October. So maybe we can touch base at that point, and we can give you performance numbers.
Thank you.
Drew Wingard from Sonics. One of the challenges in SoC designs is often the case that the traffic profiles are very dynamic.
Yes.
So how do your optimization algorithms deal with the fact that, as we've seen in some of the presentations earlier today, there are several dozen interesting use cases with very differing traffic requirements?
Yeah, that's a very good question. Actually, we get this question all the time at our customers. So to address this concern, what we have done is the way we have designed NoC Studio is NoC Studio can take multiple traffic profiles. You can provide as many traffic profiles as you want, and you can specify to NoC Studio that these two traffic profiles will not coexist at the same time. So you can basically provide subsets of traffic profile that are kind of independent. And once you specify all the traffic profile information, we will generate an interconnect that will satisfy all the requirements of independent traffic profiles and still is kind of efficient. So it will be a trade-off. If you have two traffic profiles that are kind of orthogonal, then you will not get the most optimal interconnect, but you'll still get an interconnect that will satisfy requirements of both traffic profiles, and it will be correct by construction all the time.
Okay. And do those algorithms take into account memory behaviors?
Memory behaviors such as, right now...
The performance characteristics of DRAM are enormously dependent upon address behaviors.
Yeah, sure. So when you specify traffic profile, in the traffic profile, you can specify the bandwidth characteristics of every interface that you're connecting to the NoC. So you can specify the behavior of interface such as average bandwidth, peak bandwidth, jitterness over there, latency constraints. So different traffic profile may have these different characteristics. So if your memory is behaving differently under different conditions, then you have to reflect that behavior in our specification in the different traffic profiles, and then we'll be able to take into account those.
So we have time for 2 more quick questions. So quick questions, quick answers.
Sure. Go ahead.
Hi, I'm Guangyu Shi from Oracle. I just have a probably naive question. So we usually, after we optimize the circuitry with chip circuitry with automation tools, there's always room for improvement with manual optimization. I just want to know that after using your tools to optimize the interconnect and floor plan, is there any room for manual improvement, or is absolutely the best optimized choice?
Yeah. Sure. That's a good question again. So again, we cannot guarantee that our solution is the most optimal solution, because the kind of problems we are dealing with is most of the problems are NP-hard problems. So I mean, of course, we believe that our solutions are optimal, but it might not be the most optimal solution. Therefore, we provide all the hooks to customer to further customize the NoC. So you can change everything that NoC Studio has generated: topology, architecture, routing, everything is customizable.
Thank you.
Dejan Markovic, UCLA. Is your methodology scalable to fine-grained networks such as those found in FPGAs? And have you tried to see if you can get substantial area reduction?
Yeah. So I was just talking about that with Ralph. That's a good question again. So my personal belief is that yes, it can be used. If you look at FPGA, a large part of the cost of FPGA is wiring. So using a NoC solution, you can basically reduce the amount of wire. But of course, you have to integrate NoC solution in the right way to the FPGA tool flow, because FPGA has very sophisticated software stack and tool flow. So we have been talking about that with Ralph, actually.
So Alan, you have a quick question? Very good.
Okay.
So Sailesh is available for further discussion afterwards, of course, as well.
Sure.
So we have our final presentation of the day. I'm quite excited about this presentation. It is by PLX Technologies. I get my notes out here. The speaker is Jack Regula. Jack has been working on VME going to PCI and now PCI Express related technologies for a very long time. And so PLX is now working on getting basically PCI-based switching technology into the racks, so data center rack space. Instead of following proprietary routes like some companies are doing in this space, PLX is really pushing and basing everything on PCI Express, and Jack is going to give us an overview of the switching solutions and that are forthcoming from PLX.
Thanks, Ralph. Thanks everybody for staying so long to listen to me. I'm going to have to race right ahead to get through all my slides, if I can figure out how to advance them. Ralph? Oh, I got the wrong one.
Oh. You can just use this button over here.
So let me first take a moment to acknowledge my co-architects, Manny Subramanian, Jeff Dodson, and really the whole team at PLX, because it's one thing to conceive something like this, it's quite another thing to turn it into a product. But with that, let me race ahead. So we want to make PCI Express the converged fabric within a rack. And the reason we can even think about doing that is that because PCI Express is to servers like Ethernet is to the rest of the world. And therefore, you can indeed do that. We're not seeking to replace Ethernet, but we're saying that we're going to change the point where you bridge to Ethernet. Instead of bridging at the individual server level, we could say you could perhaps do it at the individual cabinet level or maybe at the top of the rack. And when you do that, you then have the opportunity to share other kinds of endpoints. In particular, you might want to share expensive SSDs. And you can move a lot of, let's say, auxiliary or I/O out of your blades and into some shared space, and approach that ideal of densely packed servers where the server blade is just processor and memory. So the benefits of a PCI Express as a rack-level fabric are that it saves cost, space, and power within the blades by removing the NICs and the HBAs and even disk drives from them. And then you get low latency, high throughput IPC at low cost power area, almost as an unintended side effect. The competition for doing this is again, data set and Ethernet. And Ethernet is at that point on its learning curve where the 10 gig LAM is affordable. The technology is moving to 40G and 100G, and I guess you'd say that in InfiniBand QDR, 40 gigs is already here, but it's 10 gig that's affordable. Now, comparing PCI Express Gen 3 to that, take an X8 Gen 3 link, it has 1.6 times the bandwidth of the QDR link, but you don't need host channel adapters to implement it. Now, why hasn't this been done before? And actually, it has. We've demonstrated this kind of thing with non-transparent bridging. That's the old way of doing multiple hosts with PCI Express, and it works. The problem is there's a change in the programming model, and if you do it that way, you have to change drivers, and that's really an untenable problem. There are other problems with Express. It doesn't support redundant links well, has limited scalability, and maybe a non-transparent bridging has always had marginal security. So all these things need to be worked on. The challenge is to do that while retaining 100% PCI Express compatibility so that you can use the existing infrastructure. That's the whole point of it. But Express has vendor-defined extension mechanisms like messaging, vendor-defined DLLP, and end-to-end prefixes. So you can do that, and you can do that without changing the programming model, so the BIOS, the drivers, the OS, the applications, none of them have to change. Then there's the non-technical challenges. PLX already has been shipping for some time a 96-lane Gen 3 switch without the Express fabric features. For this new product to be economically viable, we have to add those features at just a marginal increase in cost. And we have to do that within the normal tight schedule and budget constraints. So again, to summarize our goals, we want to be able to share endpoints. We want high bandwidth, low latency IPC. We want to extend the scalability, and we don't want to have to change any existing software. So we'll do that by using only standard Express TLPs on the edge links, and we'll have vendor-defined extension mechanisms on fabric links. And so protocol analyzers will also be able to analyze our fabric. Now I'm going to tell you this story by means of builds on a system block diagram, and the builds will make me not forget any of my points. The switch itself has 24 X4 ports plus an X1 management port, and those X4 ports can be merged into X8s and X16s according to the bandwidth needs. There's really 4 kinds of ports. We'll talk about them one at a time. At a host port, if you can, if the slide is blown up big enough, you can see that there's a block that represents an embedded NIC, and that's the foundation for the interprocessor communications. And there's also a transparent PCI to PCI bridge block, which is how a standard Express port is modeled. And in this application, the server finds the endpoints that have been assigned to it through such a bridge. There's also a management processor, and the management processor is responsible for configuring the fabric and for managing the I/O. It's really busy when the fabric boots, and after it's booted, it handles events. Events might be a hot plug event, or an error, or a fault. Now, I'm showing in this block diagram, I'm showing 2 shared endpoints. They're SR-IOV endpoints, and the VFs are color-coded, and the colors match up to colors in the P2P bridges at the host ports, and that's how the VFs are assigned. The VF can be assigned to a host anywhere on the fabric, and that's not just on the switch chip immediately above it. And then fabric itself, that could be a single chip, or it could be multiple chips in a variety of topologies. We've simplified our fabric design by using ID routing for everything. That solves a number of problems for us. In particular, it gets us scalability because we've added 8-bit domain ID to the global ID. Each domain is a separate PCI bus number space, and that gives us an architectural limit of 65K minus 256 nodes, each with 256 funds. The reason I'm subtracting 256 is we're reserving 1 domain as a broadcast identifier, and The reason you might have 256 funds, each fund is a virtual integrated NIC, and you might want to have multiple integrated NICs for each host port, so you can assign one to each VM running on that server. Use of ID routing exclusively allows us to maintain producer-consumer ordering over redundant paths. In PCI Express, memory request TLPs are routed by address, but their completions are routed by ID, but they take the same path because there's only one path. When there are multiple paths, to get them to take the same path, you have to route both types of packets the same way. And then you can configure the fabric so that different streams take different ordered paths, and then you can use all your paths. You can balance the usage on all your paths. ID routing simplifies and in most cases eliminates the needs for mapping between address spaces. And finally, we implement ID routing by adding a vendor-defined ID routing prefix, prepending it to a TLP if the TLP is not natively ID routed or if it's crossing between domains. So the prefix includes domain numbers as well as the destination bus number. Another problem you have to deal with in the fabric is congestion. There's nothing in standard PCI Express to deal with congestion. We avoid it with a pull protocol. We push short packets in host-to-host, but we pull long packets, and that naturally avoids congestion because you don't pull more data into yourself than you can sync. And furthermore, the completions to the remote reads of the pull protocol are unordered, so you can send them on any of the redundant paths, and that allows you to spread the traffic over redundant paths and ultimately to load balance on them. And if you load balance on your redundant paths and you've got equal cross-sectional bandwidth, you've achieved non-blocking. We have a beacon to signal next hop congestion, which is a signal to avoid a path with congestion. Now, some of you know that beacons work well with limited depth fabrics, but not so well on a very deep fabric. But recall that our market target is rack scale, and we can reach rack scale with a 3-stage fabric. And a beacon sent back from the central rank of a close network is exactly what we need. We also have credit-based flow control for our DMA work request messages, and that's one of the things we do to avoid deadlock. We support quality of service with TC queuing. So we have support on a narrow link that's only X4. We have 4 TC queues. On X8s or X16s, we have 8. We can do a mix of priority and round-robin scheduling from those TC queues. And we can get the benefits of traffic separation even when we're talking to a standard endpoint like a root complex or an I/O device that only has one virtual link. And one of the tricks for that is we make sure that when there's very limited credit, we only send the very high priority packets. So let's talk about our DMA controllers, our integrated NICs. Each 16-lane, which could be up to 4 ports, module of the switch, includes a hardware messaging engine. This is virtualized and presented to the servers attached to the switch as multiple VFs. Each VF is an RDMA NIC, and it can be assigned to a system image or a VM running on that server. Transfers can be done in 2 modes. There's a NIC mode that tunnels Ethernet. You read a transmit descriptor off a transmit queue, send the message, and it's stored into a receive buffer where the received buffer descriptor comes from a receive queue. There's an RDMA mode that uses the OFED stack, and as you know, that's a secure and reliable zero-copy transfer. All these transfers work by the exchange of PCI Express vendor-defined messages on the fabric links, but just standard PCI Express memory requests on the host links. And again, short packets are pushed, long packets are pulled. That pull protocol does require an extra round trip through the fabric, but that, again, since we're targeting rack scale, that's a limited penalty, and the benefits from avoiding queue delays by avoiding congestion more than pays for it. So I'm going to give you an animation of a short packet push. It starts when the host writes to a DMA doorbell. That triggers the DMA controller to read a descriptor off of transmit queue. The descriptor returns to the switch, and it's morphed into a work request vendor-defined message, which is ID routed through the fabric and hits the destination DMA controller. It's from a source VF to a destination VF. At the destination, since it's a short packet push, it's simply written into the destination receive buffer using a descriptor pulled off a receive queue at that end. And after that write, there's some handshaking. And this doesn't build in quite the correct order, but when it's done, I'll tell you what happens. First, there's a write to a receive queue, and then there's an optional 0-byte read that can flush that data through into memory. If you're tunneling Ethernet, you don't care about that, but if you're sending data in a storage application, that's very important. But after the 0-byte read completes, or the axe for the write, then you send a transmit completion queue message back across the link to the source, where it decrements a counter, and there's a limit on the number of work requests outstanding, which is a flow control mechanism, a congestion avoidance mechanism, and then there's a write into a transmit completion queue, and finally moderated interrupts on both transmit and receive completion queue writes. So we moderate both in time and number of packets, so we minimize the interrupt burden on the communicating host. Now, the pull protocol starts in the same way with the write to the DMA doorbell, but now when the completion, to that descriptor read returns to the switch, it goes across the fabric again as a work request message, but the contents is a descriptor. In fact, it's a gather list, and the gather list contains up to 10 pointers and says read up to 65 kbytes at each of these up to 10 pointers. And so with one message, you can pull a large amount of data. And this bubbles through a queue at the destination, and then then remote read requests come back the other way. And there could be many of these, but I'll just show you one of them. When the remote read request gets morphed at the host into a standard read request, partial completions come back. Again, I don't build it in quite the right order. I don't have a PhD in PowerPoint. And we combine those short partial completions into 512-byte fabric completions. It's a standard PCI Express completion going through the fabric, ID routing. When it gets to the destination, we might have to segment that 512-byte write into 128 or 256 or even 64, depending on the maximum payload size supported by the chipset at that end. And then we have the same handshaking as before with the receive completion queue write, the 0-byte read, and so forth, and then transmit completion queue message going the other way. Now, this is the NIC pull mode. If it were RDMA pull mode, it would look exactly the same, except instead of reading receive descriptors off of receive queue, we take a buffer tag out of that descriptor that we received and read a buffer tag table up in host memory twice, once to validate security parameters in the message, and a second time to find out the actual destination address to write the data. But these reads of local host, destination host memory are masked by the read of the remote memory, so they don't impact performance. And because of that, we don't have to have really huge tables on the switch to support RDMA. We can keep all that information up in the server and save costs. It's one of the things that enable us to do this. So again, changing the subject to fabric topology, our routing mechanisms, and there's logic around small tables, is really topology independent. We focused our analysis and support on popular, a short list of popular topologies like fat tree, in particular, 3-stage close gets us to rack scale. There's a 3D fat tree. There's mesh and 2 and 3D toruses. You can also implement those. I'm going to use the 3D fat tree, which is something I came up with to illustrate the domain concept. Each domain is something that can stand alone. It has its own MCPU. You can share I/O within a domain. You don't want to get the I/O device too far away from its host, but you can communicate host to host across multiple domains. and you align domain boundaries with packaging boundaries. So a domain could be one cabinet that fits in a rack, or it could be the entire rack. So here's a picture of a 3D fat tree. The domains, the cabinets within the rack or whatever they are the horizontal planes. The inter-domain switching is going vertically in the center. Now, you can derive a non-blocking domain fabric from a 3D close, for example, by deleting one column of switches and taking the links that used to go to those now missing switches, running them to the inter-domain switches instead. That doesn't change the cross-sectional bandwidth, so it doesn't change its blocking characteristics. And then you can extend that to deeper fabrics. Here's an example of a rack-scale domain fabric. It's 2 columns of switches. It's a total of 12 switches generating 72 X4 ports. And I know you can't read it, but there's not much I want you to take away from this. If you want to go anywhere within the domain, you go from the edge switch, you bounce down to any one of those the bottom row of switches, and then bounce back up to your destination. If you're going inter-domain, you go through the bottom row switch, through an inter-domain switch, and back out to some other edge. Here's perhaps a more interesting one, a microserver aggregation fabric. The blue box on the left is one switch, the switch that might be on the blade itself, and it's showing ports for 14 microservers plus 4 shared I/O devices. It shows 2 X8 links going into the fabric. The domain fabric is on the right-hand side of the diagram. It's really 2 redundant halves. It's all X8 switching. And there's 4 shared I/O slots in there, or at least that's what you could plug shared I/O devices into them. And if that's where you plugged in network adapters, or NICs, CNAs, and that was how you wanted to do your communication with the rest of the world, that's all the fabric that you would need. And you could talk to other domains and servers anywhere via Ethernet. But if you want the benefits of the low latency IPC, the RDMA over PCI Express, you need that second column of switches on the right, and you need to connect to other domains. So with what I've drawn there, and it would be possible to mesh 4 of these cabinets together. That would be a blocking configuration, because mesh typically block, but you don't need a top of rack switch. If you go to a top of rack switch, you can achieve the non-blocking condition through multiple domains. Now, I'm showing 18 X16 links going inter-domain. For non-blocking, you need to use all of those, and each one of those could go to a single 6-port, 6X16 ports, and connect 6 of these together. Now you could bifurcate those into 12 X8s, and do 12 of these boxes. Whoops, I went too far. And you could bifurcate again into 24, doubling the number of ports again, and get 24 domains. And you're already well beyond rack scale. We could stop there. You could also, each one of those could go into a close network, and you could have, well, tens of thousands of nodes. But again, our market focus is the rack scale, and what limits us to rack scale is not the scalability limit of the fabric so much as the amount of on-chip buffering and so forth that enables us to master the fabric latency and achieve nearly line speed throughput. I'm racing through these slides and changing the subject abruptly. I see I'm running out of time. So how do we do this without changing any of the existing software? It requires some management CPU sleight of hand. So any software that doesn't exist has to run on the management CPU. If we're running it anywhere else, it's changing the game. So what the management CPU does is it manipulates the fabric and I/O configuration space to match the standard enterprise I/O programming model. So the way we present configuration space, when a host does enumeration, it sees a single level of standard PCI Express switch with the endpoints we've assigned to it at downstream ports of that virtual switch. Now that takes, to get to that point, the MCPU has to configure mapping and routing tables in the switch, and it does this transparently to host software. We also have to fool the management processor itself a little bit because we're using Linux as the OS on the MCPU, and it doesn't know anything more about how to manage our fabric or host ports than an instance of Windows running on a server would. So we don't provide a configuration space for those. We have memory map control registers that are dealt with by our own management application. We also leverage existing software infrastructure to a maximum extent by using TCP/IP stack for Ethernet tunneling and OFED stack for RDMA. And so by doing that, all the application that use the standard network APIs can run over this fabric without change. Now, on the next slide, I'll show you a standard software layer diagram. The green boxes are modules developed by PCI Express. They're either driver layers or adaptation layers. In particular, on the right-hand side for RDMA, we're implementing the Open Fabrics verbs as well. Oh, I don't have time to dwell on that. So let me say a few words about our shared I/O mechanism, and then go into some performance figures. Well, we can share I/O by the assignment of the VFs of an SR-IOV endpoint, or the functions of a multifunction endpoint, or even the one function of a standard single function endpoint to a host or hosts on the fabric within the same fabric domain. So that's the specific intent is to share SSDs within a fabric scale cluster, to share the NICs or CNAs used to connect into the cloud. But we can also do things like create a GPU fabric where you have a fabric that's primarily graphic processing units at the nodes, and they're communicating with each other directly in memory space or via RDMA, and by the means of these peer-to-peer transfers, you're eliminating the host as a bottleneck, and you have many more GPUs per host than you can have any other way. So here's the model for sharing an SR-IOV VF. On the left, you have the management system. On the right, you have a server. So in the management system, there's a PLX management, CLI, and API that are exposed to platform management. There's a PLX management driver, and then there's the vendor PF driver, all running on the MCPU with an SR-IOV enabled Linux kernel. On the right, you have a vendor's VF driver controlling the VF of a shared device, and that can be an SR-IOV aware or unaware operating system. But basically, to summarize, the VF drivers from the vendor runs on the host, and the PF drivers run on the MCPU. Now, we've done some hardware performance benchmarks in Gen 2 and again in Gen 3 to see what kind of throughput we can get. At roughly 11% CPU overhead with 2 back-to-back servers through non-transparent bridges, we got 22 gigabits per second. Comparing that to 10 gigabit NICs, which unsurprisingly did just about 10 gigabits. That's more than twice the throughput for the same received CPU overhead. And that was at a latency of 25 to 30 microseconds. The PCI Express was marginally faster. And of course, with the new hardware we're talking about here, we'll get lower latency, especially using RDMA. Now here's a system hardware latency chart. Let me take a look at it and see how readable it is. It shows several different ways of doing a transfer through the fabric. Up in the top left, we're talking about a PIO write. In the old days, this would have been non-transparent bridging. Now we're talking about tunneled window connection, which is replaces non-transparent bridging to support the IID routing paradigm. And so you can do a write, and this is with one stage, 3 stage, or 5 stages of fabric. So that varies from 227 to 827 nanoseconds. For a PIO write, and the PIO writes are still available to you. You can access them through an MPI driver. Then there's the short packet push. which, okay, this is not a laser pointer, which does 680 nanoseconds through a single stage and 980 through a three-stage fabric. And finally, the PUL, which is 1.8 microseconds through that three-stage fabric. So, you know, for rack scale, we're under 2 microseconds of hardware latency, and the software latency is whatever it is. I can't talk about that yet. And then finally, we simulated throughput versus payload size for a number of different parameters. There's two curves there. The bluish curves that start out higher are the short packet pushes. I guess they're yellow and orange. The curve that starts out lower is the PUL protocol. We can push 116 bytes in a single short packet push. If we do multiples of those back to back, we can do longer. The crossover is just past 200 bytes, so that's if you can send your message with 2 short packet pushes back to back, do that. If you're going longer, use the PUL protocol. And this is asymptoting out at around 25 gigabits per second on an X4 link, where wire speed is 32 gigs. So that's around 75% best case. And the different curves have to do with whether the RCB of the servers at each end. We're plotting results for 64-byte and 128-byte RCBs, but we're starting to see chipsets that can do 256 bytes and would do slightly better. And they also vary according to whether you're just transferring one direction, or you have at each node you have reads and writes going, transfers in both directions at the same time. Now you're limited by the host link bandwidth, because the host link has descriptor reads and completion queue writes on it, in addition to the fabric traffic. And so that means the fabric, as a result, is operating with some overspeed, and then supports our contention that the fabric will be low latency. And so that just about does it. I'm open for questions. I apologize for having gone so fast. Maybe I can make up for that with some questions.
Yeah, also thanks for coming here despite having a really rough voice or throat. So thanks for doing this after all.
Yeah. Thank you very much.
So perhaps you can comment on current status, and can you share anything in terms of where your switch is actually potentially being deployed in a test cluster?
There's a little bit I can say. So we're going to tape this out by the end of the year, and we'll be sampling it early, first half next year. We're working with some companies who are developing systems in parallel with us. I forgot to mention that this chip will be pin compatible with the unfeatured chip that we're bringing that we already have in production, just about in production. So if somebody could build a system, do their hardware signal integrity, and get things working with the first generation of hardware, and then they can add the features, and that will definitely speed time to market. So we expect that you'll see systems with this chip in it by the end of next year.
Thank you, Jack.
Thank you.
We have Jan Willem, who's going to share just a few more logistical details, and otherwise, we thank you for attending the first day of the conference.